Hey, this is Leach with Simpson Math, and in this video I'm going to be talking about random variables, specifically discrete random variables, their probability models, how to get their mean, aka their expected value, standard deviation, variance, and I'll show off how we can do it using technology. So let's get started with a few kind of definitions. So first, what is this random variable? So we're still in the world of probability. Variables, when you think about it back in your algebra days, it's like, oh, it's this x, and I need to solve for x. Well, not quite anymore. So the variable here is it's still the idea that we have this variable. It can be other numbers. It's because it's going to vary from some value to another, and it varies randomly. We don't know what its output is going to be, but we do know kind of at which rate it produces each of those outputs. So here this says that a random variable assumes any of several different values, aka numbers, as a result of some random event. Random variables are denoted by a capital letter, such as x. So what's different than this than maybe some previous probability is our output from these random variables is a number. So we need to make sure that the random outcome does produce a number, because we can eventually find the mean of these numbers, the standard deviation, the variance. We can draw distributions to see what they look like, so forth. And like I said, we're going to use a capital letter like x. So there are two types of discrete random variables. This video is going to focus on the discrete one, but just to be aware of the differences. So discrete random variables, and this is spelled C-R-E-T-E. The C-R-E-E-T version of the word discrete is like, I'm a spy, don't tell anyone. This discrete is separate and apart. So when the values are a countable list of possible values, possible outcomes, this is a discrete random variable. So it's like I have some number line, and so our possible x's is this one, and this dot, and this dot, and this dot. It can be a half, whatever, but these are separate numbers. There's nothing going on between this space. Versus a continuous random variable, so when the values can be any value, possibly bounded on either side. So maybe an example of this is not necessarily the dots arranged here, but I think of shoe size here. So if I was to enter a room and I was to have everyone tell me what their shoe size is in American male shoes, because American female shoes differ whether it's European or American, whatever. So American male shoes, what's that size? It's like what those shoe sizes are. I don't know how small they go. Maybe let's say fives, 5.5, 6.5, 7, on and on up. Once it gets to the bigger shoe sizes, this halves kind of stop. We have 12, 13, 14, so forth. So notice there's no pi, like pi, 3.14 shoe size. There's no 12 and 3/4 or 6.923. Those aren't a thing. So it's just specific numbers. But a continuous random variable would be like the size of our foot. So let's say I was to put my foot into some measuring device. Let's even say it's super fancy, measured with lasers, and someone says that, oh, your foot is 11.239 inches. Yeah, I said niner. That's the continuous, where it can be basically any number, maybe between here and here, or any number, whatever. Typically, they're kind of bounded intervals of possibilities. All right. So then our probability model. I've previously talked about probability models, so this should feel pretty familiar. It's a collection of all the possible values and their associated probabilities. The main thing here is that, again, our output from these is a number, not just the color red, but that red might need to be associated with some sort of number or something somehow appropriately. So recall that for valid probability models, each probability needs to be valid, aka between 0 and 1 inclusively. These are also non-overlapping events. So there are disjoint events from one section to another. They're all disjoint, they're non-overlapping, and the sum of all those non-overlapping probabilities is 1. So the example I want to talk about real fast is roulette. I don't want to go too much into roulette, a little bit, but just a little bit of just the idea. So remember, we have it's the croupier, that's the dealer, but they don't have cards, so they're the croupier. They'll drop a little marble, it'll spin, and then eventually land on one of the things. So here I kind of drew it landing on black 24. So there's a few ways that you can bet. So when you go to a casino and you join a roulette table, you'll be given a set of colored chips that will match, that will say that to you. Someone else will have a different color or a different pattern. So you can place these chips on anywhere on this table. The grouper will know that it's you because it matches your colors or your pattern. So the most easiest bet is to bet on any of these on this outer side. Those are the 1-to-1 bids. So if I bet, oh, I think it's going to be an even bid. I'm sorry, an even number like this 24 was. I could put my chip on here. At each table, each chips are kind of worth a different amount. So there's like the dollar table. That's where I would live. The $10 table, the $100 table, where each chip is worth $100. But let's say I'm just playing with a $1 chip, and I place down my chip here on the even, and I win. Then I will. If you win, you always get that chip back. But before you get that chip back, the croupier will give you whatever your winnings were. So in this case, it's a 1-to-1 bid. So because it's basically a 50-50 chance to win. So if I win, the croupier will give me a second chip, but that's a net gain of 1. So don't worry about that chip coming back to you, because if you win, it comes back to you. Worry about what we're gaining. So we're going to gain 1. But if I bet on this even and I lose, well, then that's just going to go away. I'm going to lose that $1. There's a lot of other ways you could bid. The one that we're going to talk about today is the corner bet. So if I put a chip right here in the corner of 4 of our values, I'm betting on these 4. This is an 8-to-1 bid. So if you notice, ignoring the 0-0-0 for just a second, there are 36 slots. And so that's where they come up with the 1-to-1 probability for the evens. If you notice, it says right here 2-to-1 for those columns. So if you place here and win, pardon me, your $1 becomes $2. So you gain your $1 back that you bid, and then they will get 2 new chips. That's a net gain of 2. If you lose, of course, you would still just lose your 1. You don't owe the croupier any extra when you bid a different number, or sorry, when you bid higher. So this is an 8-to-1 bid. And basically, if you think there's four squares that could be a winners out of 36-ish possible things, so that's an 8-to-1 bid. So if I place my chip here and a 1, 2, 4, or 5 show up, I win. Anything else, I lose. Now, see the 0-0-0? That's how the house makes their money. Because notice if I bet an even bid, even though mathematically I would say 0 is even, we would lose. The only way to win on a 0 or 0-0 is if you specifically bid on it. And you can bid on it directly by putting a chip on the 0. If you were to put a chip right here, you would be bidding on the 0 and the 0-0. You could put one here to get this triangle of 0, 2, and 3. The only way you could bid 5 in the game is by putting a chip like here, and you're saying, I want these 5. Like if you put one here, it would give you these 6. Put it here, it would give you these 3, so forth. I'm rambling now. Okay, so our problem is we're talking about these corner bets. So as I could bid these 4, that's how that works. So we're going to define our random variable to be capital X. You can pick whatever letter you want, but we typically will, by default might stick with the X. And try to aim for it to be capital. It's the net result for a $1 corner bet. That's my 4 numbers in American roulette. So my probability distribution is this. So I'm going to label my top row here as X, my second row as the probability of X. This is my capital letter, but then when I mention my specific possible outcomes with my probabilities, we usually use that lowercase x. It doesn't really matter. So if I win, I'm going to win $8. I get my 1 chip back plus additional 8, so that's a gain of 8. There are 4 ways I could win that on these, wherever I did the corner bet. If I did the corner bet, sorry, it's going all over the place, right here, then that would still be 4. So whatever 4 I bid on, I have 4 chances to win, and it's not 36 because it's 36, 37, 38. There are 38 total slots on this wheel, so that's why it's 4 out of 38. All right, then there is 34 out of 38 chances to lose. So there are these 32 numbers that I could lose on, plus these additional here, 30, these additional, they're making 34. Notice if I add these together, sorry, let me just rewind. So first, are my probabilities valid? Yep, they're both between 0 and 1. Are they non-overlapping? Yes, they're non-overlapping. I cannot win and lose on the same chip. Then if I add these together, do I get 1? Yes, I do. I get 38 over 38. So this is a valid probability model. So let's say I sit there placing just $1 corner bets over and over. It could be the same for, or it could be different for. It could move around, doesn't matter. But as long as I just keep placing $1 corner bets over and over and over and over again, on average, how much do you think I would have win or lost per round, let's call it? Well, let's basically find the mean. In random variable talk, we call that the expected value. So the expected value of a discrete random variable is the average, or typically more appropriately, it's the mean of a random variable. So it too is the physical balance point because it is that level of a mean. It's the theoretical long run average. So if I, maybe not just me sitting there all night, but if I had a robot sitting there playing roulette for infinity, I mean, you can't quite get to infinity, but approaching infinity, on average, how much was he winning or losing per game? We typically denote it by one of two things. We can do E of X, so that's just E for expected value, just like our probability of whatever, we're just using E for expected value, E of X, the expected value of X, or this mu symbol. So this might be new to you. So mu is the population mean. So this is a Greek letter, lowercase Greek letter mu. Actually, if you look at our Simpson Math logo right there, the Simpson Math logo, that is an integral and then a mu symbol because we're nerds like that. So it's not really an SM, it's an integral and a mu. So this mu, we're using to represent the population mean. So let's say I wanted to find the average number of hours that my college students are taking. I could ask my class, hey, how many hours are you taking? How many hours are you taking? How many hours are you taking? And I could find that number and average it, but that would be my sample mean. Recall that's X bar. But if I went to my college registrar and I said, hey, I'm doing some data collection thing and I'm curious, how many, what's the average number of hours that all of our students are taking? They could run a list and find how many hours that all of our currently enrolled students are taking, average them up, and that would be the population mean. That would be the mu of all the students at my college. Just a note on how we draw that. This is I think of it as a lowercase u, it rhymes, lowercase u, but then we have this tail on the left-hand side. I draw that by starting at the bottom and then swooping up and then just drawing that lowercase u. That's a bit exaggerated tail, so just something like this. Try to avoid it from being an m, especially not that. That is clearly lowercase m. So it's basically, again, a lowercase u with a swoop. So whoop, like that. All right. So what is our population mean? What is our expected value formula? So it can be mu or E of X. Doesn't matter how you want to write it. And then we have this. Remember that capital sigma is the sum of my X times my P of X. Okay, well, what is that? Well, P of X is the probability of X, so that, and then my specific X's. Right, so it's a specific X's times our P of X. Sometimes you might see subscripts on it, where like this could be X sub 1, and this would be P1 or P of X1. This would be X2, this would be P2, so forth. That's also kind of a thing. So let's find our expected value for that $1 corner bet. So my first X is -1 times its probability of 34/38. Plus, because we're going to find the sum of them, my second X, which is 8, times 4/38. So it's just this, a little far away. -1 times this, plus 8 times this. If there are more, you just keep adding and multiplying, adding and multiplying. When we do, we get a nice little fraction of -1/19, or just over a nickel, -0.05. Remember, we're talking about money here, so you're losing on average a nickel, which is because the house has an advantage. It's like, okay, well, the house makes a little bit more than a nickel every time I play. Yes, I mean, on average, but if you ever go to a casino, there are a lot of casino tables, and all those tables are running this same sort of process, and not all of them are $1 as well. But so, you know, all day long, 24 hours a day, 7 days a week, 365 days, multiplied by however many tables, constantly running, that nickel every time on average really adds up. Now, that's how functionally how we do it. And really, we're going to be using technology anyway to do this. But I find this helpful to kind of process this as a bit of a learning example to see that all we're doing really here is just finding the mean. So let's take a look at this. I could, another way of thinking about this process is imagine that I'm going to put my corner bet here. I could win 8 here, 8 here, 8 here, 8 here. And all the others, I would lose $1, lose $1, lose $1, lose $1. So if you look at this, I have 34 total negative ones and 4 positive 8s. So let's just average that together. So how do you find the average of things? Well, we're just going to add everything up, divide by my number of things. So I'm going to say I have a -1 plus a -1 plus a -1 plus my negative ones, 34 total negative ones. And then plus 8 plus 8 plus 8 plus 8. So I have 38 total things, divide by 38. So you see that this literally is my mean. Add up all the things, divide by the number of things. Since this is from our population, from our model, then we're using mu instead of our sample x bar. Now, obviously, this is not the most efficient way of writing that, so we can just do multiplication, right? But if I'm adding 34 negative ones, I can write that as -1 times 34. Similarly, I can write that as 8 times 4. All right. Now I want to do a little bit of a different thing. I want to unadd. So I can, pardon me, I can have this be -1 30 times 34 over 38 plus 8 times 4 over 38. If you look at my camera, I kind of think of it this way, where it's this fraction, I'm just going to unadd. So the idea is, if I had x halves plus y halves, could I write this as x plus y halves? Sure, of course I can, because they have common denominators I can add. So if I can go this way, I can also go backwards. So that's what I'm doing. I'm unadding. All right, so now that I've unadded, I'm going to finagle this just a bit. So that way my -1 is now, it's not just -1 times 34 in the numerator. I can kind of imagine this is a -1 over 1 times 34 over 38, and these two things would equal. Similarly, I keep saying that word, and it's hard to say. I can take this 8, kind of pretend it's like an 8 over 1, but just write the 8 times 4 over 8. 4 over 38, rather. And notice, this is exactly what we wrote down up here, where this is my x value times its probability plus the next x times its probability. That's exactly what we just did. And so this same idea would work if I have a lot of other different x's or potential outcomes. But so do you see that this literally is just the mean? Add up all the numbers, divide by the number of things. So multiplying by the probability does two things. It, pardon me, my throat's dry. It helps us add up all the numbers here, and then we are dividing by our total number of things. If we do that across the board, it kind of takes care of the adding and the dividing all at once. All right, so now let's talk about the standard deviation and the variance of a random variable. RV is abbreviated random variable. So the standard deviation of x and the variance of x are the standard deviation and variance of a random variable of x. So SD for standard deviation, var for variance. Recall that if I have the standard deviation of x and I want to get to the variance of x, we would square root it. That is backwards. Hence the blink, 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 blink. If I have the variance, because this is like sigma squared or sigma, so if I have the variance, I would need to square root it to get to the standard deviation, or square it to get to the variance. Sorry, that was backwards in my notes. All right, so let's talk about finding our standard deviation. Full disclosure, this is the only time, at least in my classes, that I'm ever going to do this by hand. We have technology, and I'll show you how to do the technology at the end of this video. But it's helpful to understand what it is So if you remember the standard deviation of a bunch of data, I'm so sorry. All my cups are empty. The standard deviation of a bunch of data, it is the typical distance that our data values vary away from the mean. Um, and the process that we go through is we find all of our deviations, which is distance and direction the data values are away from the mean. But then if I add up all my deviations, I always get 0 because the mean is the physical balance point. So we get rid of this whole direction part by squaring it. We add up all those distances now, and then average those. So here's the general process. Don't let it freak you out. It's a bit gross because we have decimals. Don't stress about that. So here's my probability model. Just for a little bit of color coding for this first part, I have this blue and I have this as purple. So I'm going to take my x's and subtracting from the means to find my deviations. Remember, deviation is distance and direction the values are away from the mean. So if I do -1 minus my mean, and it is minus a negative, so it ends up kind of being plus this, I'm going to get a negative 18/19, which is a negative 0.948. That means I am, when you lose, that was 0.948 below, or dollars, $0.948 below the mean. And we know it's below because it's negative. If we look at the 8 minus, really rather 8 plus the 1/19 would then be 8 and 1/19, or 8.05263. And we know this is above the mean because it has an inherent positive there. So those are my deviations. And recall, if I take these deviations, and if I did the multiplying by my probability, or add up 34 of these, add up 4 of these, I'm going to get 0 every time. That's a bit of a bummer, but remember we fix that by squaring it. So if I square my deviations, I get these numbers. Then I'm going to now find the average of these squared deviations. And we do that by adding up all of our things and dividing by 38. So I have 34 of these, and then I'll temper it by dividing by 38. And again, 4 of these divide by 38. And again, these are just my probabilities that are right here. All right, then to finish this up, to find my variance, I'm just going to add up all of these things. So follow the arrow down. It's going to be the sum of, I'm just going to find the sum of all of these. So that's this 0.8030 plus 6.8258. So we add those up, and that is my variance. So my variance is 7.6288. But the problem is this is dollars squared. So this data here is dollar. If I do my deviation, this is still dollar. Now I do square it. Now it's dollars squared. I don't know why I put the square on that side, dollar squared. Then when I multiply it, it's still dollars squared. When I add them up, these are still dollars squared. So I should square root it to put it back to its base units. So now this is $2.7620. So the typical distance at these data values, or the typical distance at these winnings, you could lose $1 or gain 8. The typical distance that they vary away from the mean of losing about a nickel is 2.7620. So just to sum up my standard deviation and variance, so my variance is sigma squared. Previously, we should have discussed this, that the population standard deviation and the population variance use the lowercase sigma. We draw it like this. So the variance of x is what we just did here, which is the same thing as the standard deviation squared. For the standard deviation, if we take our standard deviation, I could square root our variance. So it's just this same formula with a square root over it, or it's the square root of that variance. So if you know the standard deviation, you can square it to get the variance, or if you know the variance, you can square root it. We'll be needing to play this game a lot of moving around because we don't like to do the math at the standard deviation level, so with what we're talking about later in a future video, but we will be, so we have to do it at the variance level, and then we have to put it back. All right, let me show you how we do this using technology. The bummer is, one sec, let me push some buttons. This one, and this one, and then I push this button Ta-da. The bummer is that for Desmos at least, it doesn't have it built in. So I have built a calculator and it should be linked in the description below. So I built this Desmos calculator so you can fill in the blanks and get your stuff if you're able to use Desmos. So let me do Desmos first and then I'll do Excel. So admittedly, I mean not Excel, the 84. Admittedly, the 84 is probably a little bit easier. It's the one thing that I say that kind of beats Desmos out on this just because it does it natively. So on here, I'm going to make this be a bit bigger. There we go. So we're not using the graph or anything right now. So edit the table as needed. So I'm going to come through here and delete out my x's, deleted, and I'm going to type in my two x values. I could lose 1 and I could gain 8. I need to come over to my probability. Notice I have labeled it P1 instead of Y1, just so we're talking about probabilities. Ignore the subscripts. That's just because we only have, it's our first table. The ones are for it's the first table, the first instances of the x's or p's. So there's a 34/38 chance of losing $1, and there's 4/38 chance of winning $8. So there's my probability table just written vertically. All right, then make sure it's out from behind me. Then, so this here is just to make sure that we have added this up to 1, that my probabilities add to 1 as they should. Great. All right, here I'm saying that M is the expected value, the M for mean, the V is for variance, and the S is for standard deviation. So this formula should look a bit familiar. It's the sum of my x's times their probability. I had to do some Desmos things to make it happy. Don't stress about all that coding. I mean, it's not really coding, just math talk. So the mean here is that negative 0.0526, which we saw in the notes. Then for the variance, I'm doing the same thing. Notice this is the deviation, the x's minus the means, the mean specifically, squaring it, times the probability, and then we're going to add it all up. In case you're curious, we need an index when we do the sum. And so I'm saying start at 1, start at the first one. But I can't use in for both or I for both because for some reason Desmos got mad when I did that. So here's why I'm using ins and then i's. Shrug, don't stress about it. So now that we have our variance, how do we get the standard deviation? Well, we just square root it. So if you use this, and my students, I'm cool with using Desmos, probably unless future me has changed my mind. But this is a way that you can do that. You can save this as a copy, so that way you can add that to your account, and then you can pull it up when you need it. So that's how we do this on Desmos. Obviously, if you need more digits, more things, just make that bigger. All right, let me show you how to do this on Excel. I keep saying Excel. I should probably open up Excel and do this. I was planning on do this on the 84 though. So let me do my, I need to type in my data. So I'm going to press stat. Ooh, let me make you see the big screen. There you go. It's a bit bigger. So I'm going to press stat, then edit. If there was something in here, remember you would arrow up to L1 and press clear. Do not press delete. If you press delete, the easiest way to get it back is probably do second plus 712 and clear your calculator. But if you do, you can press second delete to insert it back and then type in the correct heading. All right, so I'm going to, in L1, I'm going to type in my numbers, -1 and 8. Just press enter or down arrow to move between them. And then make sure they're lined up horizontally. So I have 34/38. And then I have 4/38. Don't freak out. The 84 will convert it to a decimal, but it converts it to a lot of decimals. So that way it's still pretty accurate, but it does do that conversion to a decimal. So don't stress about that. Press second mode to quit. Now we're just going to run one var stats. So stat, calculate, one var statistics. I know we have two columns, but that second column we actually do as a frequency list. So here's my L1, then my L2 is my frequency list. My headcanon about why this works, if you go to some other internet kind of calculators and do something like this, it often will yell at you and say, oh no, your frequencies have to be integers. Well, my theory is that it was it was a bug that they didn't make it be had to be an integer, but then it works. And so it's like, oh, it's a feature. And I think a lot of people who program in the frequency list, they think, oh, I'm going to be smart and put in this restriction for it to only allow these for them to be integers. That actually breaks it for doing it like this. Um, so notice the sample standard deviation doesn't get printed because we actually would be dividing by 0. Because remember how our denominator, when we do the sample standard deviation, the s, we divide by n minus 1. Look at what it thinks the n is. It thinks the n is just 1. It does that because if I add up my p's, what do I get? 1. So it thinks n is 1, so when it does n minus 1 to get the sample standard deviation, it breaks because it's undefined, so it just doesn't print anything. So x bar is my mean. I know it says x bar, but x bar is mean, or mu, but this will print an x bar because it doesn't know we're talking about a population. And the math for them is the same. Then no, okay, for a second, I was confused because this number is really close to my variance, and I was like, no way that's the same thing. Okay, sorry about that. And then no, so this, of course, the S is not our value, but our sample standard, so not our S, our sigma is the population standard deviation of 2.76202. Now, if I needed to get the variance, the best way is to just press second crit and type in your value into a lot of decimal places. So 2620,298, sure, that's enough. And then square it. And then out to at least roughly a good amount of decimal places, it should be pretty accurate. Do more than you think, so that way it doesn't mess up because it's square rooting, weird things happen. If you want to be a little bit more proper, that sigma is actually stored into the calculator. So you can press the vars button, which is not variance, but vars as in variables. So pick the vars, go down to statistics, because that's the class we're in. And then here are our stats. So here's the sigma x that was just calculated. If you don't trust yourself, press enter, and there is the sigma x. So if I take that sigma x and I square it, then I will get the variance fully without having to type anything in, using as many decimal places as the calculator knows. So that's a little, I don't really think it's a shortcut because it takes longer. I would just write it down myself, write it on scratch paper, and then type it in. But that's how that works. All right. I guess I'll go ahead and show you how to do this on Excel. I wasn't planning on doing that, so I don't have my Excel up. Welcome to my Windows. All right. So I didn't practice this, so I hope I remember how to do it. All right, so I'm going to put in my x's and my p of x's here. Label it whatever you want to. I use a lowercase. It doesn't matter. My x's are -1 and 8. And then this is 34 over 38, and this is 4 over 38. So, oh gosh. It auto-formatted it to a date. Thank you, Excel, for being disruptive. I'm going to press undo. I think if I, let me redo that, and I'm going to change this. So if you hit Control 1, it pulls up the format cells, or like right-click format cells. And I'm going to change this to be just a number. Let's see if that works. Just a number. And then change it back to 4 over 38. General 4 over 38. Stop doing that. No one has April 38th. That's not a thing. Fraction. Oh, that works. So 4 over 38, and it's wanting to reduce it for me because it's so kind. Cool. Okay. I don't know why it's being annoying, but whatever. Thanks for being helpful. Excel. Okay, so now basically you're going to then have to do the math yourself. Um, so the process is we're going to do a weighted mean. I should not have started this. Um, so there probably is a weighted average. If not, I'll just do the multiplication. Basically, we're just going to have to do what we did a second ago. So I'm going to do equal to um, this thing times this thing. Why does it not like that? Okay, let me turn this to a fraction. Will you now do it? Let me retype this in. 34 over 38. Okay, it didn't know that was a number, I guess. Um, so, all right, so now that it's behaving, and then I can fill down. And this is, I'm just going to call this my mean bits. So this is the part of my mean. I guess I can, yeah, this is the part of my mean here. Um, and then we'll actually get the mean right here, which will be the sum of these two. So just equal to, and I'm going to do sum, even though sum formula is kind of silly for just two things, because if I wanted to add more data values and I did an insert, then the sum is now counting for those two things, and I'm not having to mess up with that adding. All right, then let's do our standard deviation. So let's find our deviations. We're going to square them, the square deviations, and then that should be it. We'll then find the sum of those. So our deviation, we're going to find equal to, this is the, this x, this -1, minus my mean. I'm going to put an absolute reference around that mean. So you can press F4 or FN F4 or add the dollar signs manually. So that way when I fill down, it is always referencing my mean right here. All right. If I add these up, that's not going to help me with anything, so I'm not going to do that. So now let's square our deviations. So take this cell and square it, and then fill that down. Then I'm going to find my variance bits. I don't know why I'm calling it that, because I need to multiply this squared deviation times the probability. So it's basically what we just did here. So equal to this piece, this component, times the probability. I'm going to go ahead, times that, and now I'm going to fill down. Oh, it's giving it to me as a fraction 6 and 5/6. Cool. So then my variance is just going to be the sum of these parts. So again, sum of these things. I'm going to go ahead and turn this reference to be a decimal. Just say number. Give me 3 decimals. So that way that is a 4 decimals. A little bit more usable answer. And then lastly, for the standard deviation, we're going to do the square root of this number. And again, I'll go ahead and have this round for me to 4 decimal places. All right. One thing that I would do, that I like to do, if I'm making myself a little calculator like this, I'm going to bold these header pieces. This thing, I'm going to make it smaller just because it's cuter that way. There are my deviations. I shouldn't have double clicked. That's better. Then I like to highlight my inputs, give them a nice bold color. Sometimes I'll do them all in yellow for my inputs, but I have them be different colors so I know that they're different things. So that way I know this is what I need to enter. And then I'll put my outputs in like a lighter color. So here's my here's this purple, and then let's do these colors here, just so that we can see that those are my answers. A little bit lighter. Oops, the green, this one. So that way it's like these are my outputs that I'm looking for, and then these were my inputs. So just uh, for fun, I guess, what if we had a different situation? If I just pressed insert, let's say there's 4 things, and it was 1, 2, 3, 8. There's yeah, sure, let's keep that 8. And then this was 0.1, 0.25. Oh, let's change this then to, I guess let's do decimal, just number. It will still store it for me. So if I'm typing in numbers or typing in fractions, it'll be a little bit happier. And I'll turn these into decimals. So numbers with decimal places. All right, let's do 0.25. Let's do 0.3. And what would be left over? I'm doing math on the spot. So that's 4, 65, and 35. Let's do a little quick just sum p of x, sum, just to double check that the sum of this is 1. Yeah, that's nice. This should, let me just make this be, should have just be 2 decimal places. It's not too aggressive. Okay. And so then, all I need to do, because for some reason, when I did this, it didn't fill these in for me. I can then fill these in. Actually, just highlight all this and fill down. So we'll fill that down respectively. So now the subtraction and stuff that it did is already there. The fixed references are there. And so now you can build that calculator out. Again, easier on the 84, even easier on the saved Desmos. But now that you have this saved, it's pretty easy to then do the same thing. This is what I did in Desmos. So you can save that. If you need to get rid of 2 of the columns, you can delete them. Or just to go back to what we had, I had -1 and 8. And then it was 34 over 38. It's going to change it to the decimal, no biggie. 4 over 38, again, change to the decimal, no biggie. And I'm just going to make these be 0. And I can even just make these be 0. That doesn't really matter. Because it's not looking at them. Because when I do the multiplication here, it's going to cancel those out to be 0. It's going to 0 those out as long as these are 0. So you can just put in zeros for kind of however big that you need it or whatever. All right. So that was an impromptu Excel moment. Excel took longer than I wanted it to. Hope all this helped to help you understand the basics of finding the mean and standard deviation and what is a random variable. Catch me in the next videos when I keep talking when I'll keep going on about random variables a little bit. All right, take care. See you in the next one. Bye.